Okay, so I hope you had a nice Easter break. And let's try to summarize where we are, basically. And we are dealing with, as you remember, the estimation of the peak river flow. And we discussed about the annual maxima method. And this is the page where you can get the supporting material. And you remember that we completed an experiment. And the experiment, we will discuss again the experiment. I would like to make a check if every one of you was successful in completing it. And but I would like to make this check next week. So tomorrow I'm still teaching with the theoretical basis. And then next week, on Friday, you are kindly required to bring the PC and we summarize the outcome from the experiment. And basically, what we learned is to fit a probability distribution to the sample of the annual maximum flow and to check if the probability distribution is providing a good fit. And then we learned how to use the probability distribution. In this specific case, it was the Gambit distribution. We learned how to use it for getting an estimate of the peak river flow. One of you sent to me a report that she found on the Secchia River Basin on the web. And the report was describing the behaviors of the basin and was describing a flood that recently occurred. And I think this is an interesting example of looking for some more information on the web. I encourage you to do so. And if you find some more information on the catchment, you may include this additional information in the report that you are eventually preparing if you aim to present a report on the exercise when you attend the final exam. Also, this person, I don't remember the name, and found a paper on the web describing some possible causes for recent floods that occurred on the same basin, the Secchia River Basin. And let me make an attempt to find it out, this paper that one of you found on the web. And just 1 second, very briefly. I just need a couple of minutes to find it out. This is the paper. This is the paper, basically. You can see the title. The title is Evidence of an Emerging Levee Failure Mechanism Causing Disastrous Floods in Italy, Extreme Floods in Italy. And basically the paper is making an analysis to explain what occurred a couple of years ago when on the Secchia River Basin a levee failed. And the strange thing was that the levee failed when the river was not really experiencing an extreme flood. Basically the water level was still well below the top of the levee, but suddenly the levee collapsed. And then the areas surrounding the river were, of course, flooded. There was one victim. Actually, it was not really a dangerous flood, but the victim was, unfortunately, the person died because he was not really prudent. He tried to get back his belongings while the flood was already occurring. The flood in itself was not very dangerous because it was slow, so the failure of the levee was quite sudden. But then the area surrounding the river is very flat, so it took some time before the water reached the towns and the houses in general. So the civil protection had time to alert the people and to tell them to evacuate. And in this case, it was just that this person took too much time to evacuate because he tried to get some belongings back. So the question explored in this paper is what caused the failure of the levee? I think it's interesting to discuss this because it was quite a sudden occurrence. The levee is an old levee built probably about 100 years ago originally, and then subsequently heightened at several stages. And we don't have knowledge, a refined knowledge of how the levee was built. But of course we assume that they were built according to good practices, and it was quite an unusual experience that a levee, an important levee, collapsed in this way. So what could the explanation be? First of all, this paper reports some witnesses by people who saw that the levee collapsed from the top to the bottom. So suddenly it looked like the levee flattened down. And really this observation was made not just on this levee failure, because this levee failure was unobserved. But in the same day, in a nearby river, in a neighboring river, a similar fact happened. So they could see the levee suddenly lowering, but in this case, the levee didn't collapse. It was just a sudden lowering, and they had time to put some sandbags. They had time to recover it. So, basing on this observation, on this collapse, almost collapse in the neighboring river, the hypothesis that is made in this paper is that the collapse was caused by animals digging tunnels in the body of the levee. And these animals, they are typically porcupines, or I don't know how to say, let me see, because in English, here it's written in English. And in the paper this paper is freely accessible on the web. And if you want to find it, if you just Google the title, you find it if you're interested. It's quite an easy paper to read. I'm not suggesting to read it. I'm just saying that it's interesting. If you're interested in looking for more information on this catchment, this is an interesting reading, but it's not the subject of questions at the exam. So basically, there is a description of the river, and there are some pictures of the animals. So here there is a picture of the levee failure. You see the bridge here, and this guy, the author, was directly involved, and also he had the opportunity involved in this analysis, and I had the opportunity to discuss it with him. And here you see the pictures of the animals. And these pictures were taken along riverbeds in this region. And the animals are typically, let me see the names in English because I don't, is Istrix cristata, Istrix basically. And also there is European badgers, red foxes, and nutria. Nutria, the scientific name is Myocastor coipus. It's a kind of castor. And basically these animals experienced a rapid increase. The number of these animals rapidly increased in the just latter 2 decades, in the last 2 decades. And the reason why they increased is something that it's not completely fully ascertained. And an hypothesis is that the increasing urbanization forced these animals to look for their homes in the only areas where they could find a quiet environment, and therefore the rivers. Another explanation is that rivers are ecological corridors connecting the mountains to the flat areas and other big rivers like the Po River and finally the sea. And therefore, along these ecological corridors, the animals found an ideal home where they could move without being disturbed. Because if they try to move, of course, in the flat areas surrounding the river, they are disturbed by cars, by people, and etc. And the third explanation could be that these animals are protected, so it's forbidden to kill them. So basically, the hypothesis is that the number of these animals is markedly increased. Of course, this is an assumption based on qualitative observation, not quantitative observations, because it's not easy to monitor the number of these animals. But an hypothesis is that they rapidly increased, and therefore they needed to dig their homes into the body of the levees. And it's amazing that these animals are able to dig very huge holes. And to give you an idea, along the levees, sometimes we can see the holes of the tunnels leading into their internal homes. And people try to fill these holes with material in order to, with like concrete or other materials, plastic materials, in order to, of course, try to repair the levee. And in one case, they had to employ 15 cubic meters of material to get the hole filled up. So it means that, the internal digging was taking more than about 15 cubic meters of volume, which is very considerable. So what happens is that when the water level increases and water reaches these holes, water goes into the levee, and the turbulence, of course, starts an erosion process which may cause the failure of the levee. This is what this article proposes, and then they are proposing a mathematical model to explain what may happen. So here there is an hypothesis for the failure mechanism, and some more pictures, and then there is a scheme of what may happen. You see, they analyze the stability of the levee under the presence of tunnels, internal tunnels, that it's not easy to detect. The problem is rightly that it's not easy to detect these holes and internal tunnels. One would need to make a field analysis, a field monitoring, a field survey, but the problem is that the rivers are very extended, and the civil protection and also the governmental bodies taking care of rivers and levees, they don't have enough personnel to perform these very detailed field surveys. And recently they are trying with remote sensing by taking aerial pictures to see if it's possible from aerial pictures to see the presence of these holes. Okay, I found this discussion interesting, and the message that I would like to convey is that when you need for additional information to form your background or to solve problems, scientific papers may be a useful and up-to-date information that you may get. Of course, there are a lot of discussions about this possible failure mechanism, and the discussion are motivated by the fact that it's necessary to identify the responsibility for recovering, for putting these levees in a safe condition. Because of course, identifying the responsibility means to identify the bodies, the governmental bodies that should be in charge of doing that. And also, if it is definitely proved that the animals are the main responsible for what happened, it means that the number of these animals should be controlled. And this is something that encounters some perplexity by the people, because the green parties, for instance, they are very keen in protecting the animals. They don't like if the animals are killed. So it's an interesting, let's say, ecological, hydrological, hydraulic question and issue. Okay, so getting back to our problem. So basically we learned how to use the Gamble distribution and the annual maximum method to estimate the peak flow. And now I would like to continue this discussion and close it today. And first of all, what I would like to say is that there are alternative distributions that you may use. Probably I already mentioned to you this. And you can find here in my webpage a list of alternative distributions that you may use. And you may need to use alternative distributions for some reasons. The first reason is that you may look for an alternative distribution if the Kolmogorov-Smirnov test is not passed, and therefore you are forced to try another distribution. The second reason may be that you may want to compare, even if the Kolmogorov-Smirnov test is passed, you may want to compare how the estimates provided by different distributions compare each other. And this comparison is interesting because in any case, the estimate that you get is affected by uncertainty. Uncertainty that we didn't learn how to quantify. There are methods for estimating the uncertainty of an estimate provided by the Gamble distribution, but in any case, these estimates of uncertainty are uncertain themselves. So basically, one way to quantify the uncertainty is to use several different methods. This allows you to get an alternative way to estimate uncertainty. So one way is the statistical assessment. You apply the Gamble distribution, and there are statistical procedures that we didn't learn that provide you an estimate of uncertainty, provide you with an estimate of uncertainty. We didn't learn these methods because they are quite complicated. And in the professional practice, they are very rarely used. Another way to estimate uncertainty is to estimate the peak flow by using alternative methods. And you get several estimates, and you compare them. If they look similar each other, it means that, of course, you are reassured. The uncertainty is not significant. If they differ much each other, it means that there is uncertainty. And you get an estimate of it. So you may want to apply other distributions for getting a way to compare your results. I'm not getting into the details of these distributions. Of course, a different distribution means a different analytical form of the distribution, a different analytical expression for getting the estimate. It means a different number of parameters, possibly. A distribution may have two parameters like the Gamble distribution, but they may have one parameter or 3 or 4 parameters. And close the door, please, because otherwise it's a bit noisy. A different distribution means different ways for estimating the parameters. And therefore, each distribution has its own history and its own package of procedures to estimate it. Keep in mind that in R, we didn't learn how to do that, but you may download additional packages that perform the application of the distribution for you. We will see some examples in the next exercises. So here you can see a list of the most used distribution. Probably the most popular one is the GEV distribution, which means generalized extreme values distribution. And the GEV includes as a special case the Gamble distribution. If you click on this link, there is a Wikipedia description of the GEV distribution, and you will see that as a special case it includes the Gamble distribution. Keep in mind that you are not absolutely required to learn more about this distribution. The only question that I may ask you at the exam is, can you give me an example of alternative distribution? It's just enough if you say the GEV, the Fréchet, and that's it. Okay? because you know, it's not really important that you learn by memory the analytical shape of the distribution. It's just important that you remember that there are alternatives. If you remember the names, it's much better for you. But then, of course, if you need to estimate distribution, you just go on the web and see how to estimate it, and you look on the web for an R package or a MATLAB package, if you are MATLAB users, to use it. Okay, and now I would like to make a mention to another procedure to estimate the peak river flow, another method. So far we spoke about the annual maxima. I would like to remind you that the annual maxima basically requires that you get an annual flood, a sample of annual floods, and you get it by taking for each year of the observation period the highest flow. So you get one value per each year. So let me make an example. Let me depict an hydrograph which lasts for several years. So let's suppose that we start from 1990, and then here we have 1991, and then 1992, 1993. And let's suppose that we have this hydrograph. I'm just drawing by chance. Let's suppose that we have an hydrograph like that. So if we pick up the annual maxima, let me draw vertical lines marking the subdivision between the years. This is probably not vertical. So if we pick up the annual maxima, we get this value, and then this value here, this one, and this one. 4 data, because we have 4 years, okay? Now, if you look at this picture, you may see that there is an apparent inconsistency in this selection, because we are getting for the year, okay, this is beginning of 1990. For the year 1991, we get a value of the annual maximum flow, which is quite low. And you know, this is perfectly justified. It means that in 1991, in this year, we didn't experience any relevant flood. So we are getting an annual maximum which is quite low. If we look at the previous year, 1990, conversely, we see that we pick up just one value, the maximum, but there is another flood that occurred which is significant. It is significant because it is superior in terms of magnitude with respect to the flood that occurred 1 year later. So basically we are getting a sample that is including an extreme which is not very extreme, and it's excluding another extreme which is, let me say, more extreme with respect to another one that we selected. And the same may happen in 1992, where we have 2 peaks, and the second one is very relevant, but still we discard it. So some people say this is not really efficient, because we are not exploiting the whole information that is at disposal. And also, this is not really very efficient, because you see that here there are several peaks, and we are discarding some of them. And this is not efficient, because we mentioned that we have always to struggle in hydrology with data scarcity. So if we are in a condition of data scarcity like this one, only 4 years of data, it's unjustified that we discard some extremes. So the researchers proposed already in the ancient times, already more than 100 years ago, an alternative method to select the peaks. And the alternative method is called the peak over threshold. So basically, a threshold is fixed, and for instance, let me fix this threshold here. And then an horizontal line is drawn, and we get all the peaks, I mark them with crosses, over the threshold. So peak over threshold. And this is called the POT method. So the peaks are this one. And what is a peak? It's an inversion point of the hydrograph. It's a point where a rising flow commutes in a decreasing flow. It's an inversion point. And we get all the peaks. And in this case, we get, there is another one, sorry. Still visible? No. Just 1 second. There is another one that I forgot. Here. Now you see that this looks more justified because we get 1, 2, 3, 4, 5, 6, 7, 8, 9 events instead of 4. So one may say this is a very good idea. But indeed, there is a problem also in this selection method. And the problem is the independence of the events. I told you that when we fit a probability distribution to a sample, in order to determine the frequency of the extremes, there is an underlying assumption of independence which is necessary. It means that the observations should be independent, referred to different events, because we are analyzing the frequency of these events. So if I have a flood that is characterized by, it's just one flood, but then it has the hydrograph has several peaks, it's unjustified to get each single inversion point as an independent observation. This is one event, it occurred once. So we cannot select 5 observations here like the event occurred 5 times. This is not correct. This is one event. If we want to study the frequency of this event must be represented by one observation, not 5. So basically, when we make this selection based on getting the peaks over a threshold, we have to make sure that each selected data is representing an independent event. So how to do that? A first, of course, possibility is to look at the hydrograph. If the hydrograph is short, like in this case, it is easy to recognize the events that are not independent. Like, for instance, in this case, you see that this is one event only. So I should not get this observation, no. And here as well, you see an hydrograph, which is one event. We may discuss about this, okay, the last one, but for sure this one is a no-go. And of course, if we get one observation, we have to get the maximum. To characterize one event, if we get only one observation of peak flow, it should be the maximum. So this one is for sure a no-go. For this one, it's not clear. And in this case, I would say that this is a no-go. So what is the conclusion? Even if you look at the hydrograph by yourself, in some cases, it may be not clear if the observations are dependent or not, like in this case. What should one do in this case? You should look at the watershed, at the basin, you should look at the rainfall to check if this event was determined by 2 rainfall, which are far apart in time or not. Because here, of course, it's not clarified what is the distance. But if you look at the scale, it may be that the distance is a couple of months. So it may be that it is caused by 2 separated events. You should look at the meteorological condition to see if the rainfall extreme, because of course a peak flow in almost all cases is originated by rainfall extremes. If you exclude the cases dominated by snowmelt, it's caused by a rainfall extreme. So you should look at the rainfall events and look if they were generated by separate phenomena or not. So it's not easy. And also, sometimes it's not practical to make this manual selection, because if the hydrograph is very long, like 150 years, it's rare that you have a so long hydrograph, but sometimes it happens, like for the Po River, you have 120 years, 100 years of observations. So looking manually at the whole hydrograph may be complicated, and therefore it's preferable to find out an automatic way of detecting the independent events. And so there are some methods that are used to reach the purpose. One method is, first of all, not to keep the threshold too low, because you may be tempted to lower the threshold to get more data. Because of course you're working in conditions of data scarcity. The idea could be, let me lower the threshold in order to get more data. But if you lower the threshold, you increase the probability of getting dependent events. So one possibility is, to try to raise the threshold until you get a sample size that is still satisfactory. This is one possibility. Another possibility is to automatically detect the distance, the time distance between the selected peaks. And you may fix a threshold in the time distance. Like you may say, for this watershed, I want a time distance between peaks of at least 1 week. For instance, for the Po River, where the floods last typically a couple of weeks, you may say that you want at least a couple of weeks distance in order to make sure that events are independent. And this is the method that is most frequently used, because it's also easy to apply automatically. You detect the time distance between the peaks and you reject those peaks who are too close in time. Basically, these are the methods that you may apply. At the end of the story, you get a sample of extremes that you treat in the same way as for the annual maxima method, but with a different distribution, because it can be proved also with theoretical considerations that the gamma distribution does not lend itself to a reliable representation of the peaks over a threshold. So the gamma distribution, it can be proved that is efficient for fitting the annual maxima. It's not as efficient in fitting the peaks over threshold. There is another distribution that is usually applied. I'm not sure if it is mentioned here, which is called the Pareto distribution. And probably, if you click on the link here, there is a link to the peak over threshold, and probably here there is a description of the Pareto distribution. This is a general link on extreme value theory, and you can see that there is here, let me see. Yeah, here it's mentioned the peak over threshold, and I'm not sure it is mentioned the distribution. It is Pareto distribution. It is this distribution. Again, you don't need to learn it. Okay, so this is an alternative, and keep in mind that the peak over threshold method is very frequently applied in the professional practice, and almost like the annual maxima method. It's a bit more complicated because there is this question of independence that makes the elaboration a bit more, it requires a bit more of experience. And for this reason probably is less applied than the annual maxima. But they are comparable. In the professional practice, people know the peak over threshold quite well. And I'm not dedicating much room in my web page to the peak over threshold just because it's it's similar to the annual maxima. You see that there are many similarities. So basically, I'm not dedicating much room to the description of the peak over threshold for this reason, but still, don't be, please remember that it's important. Okay, now I would like to enter in a fully alternative option to estimate the peak river flow. Because so far we dealt with probabilistic methods. And probabilistic methods, why I call them probabilistic? Because they are based on the use of a probability distribution fitted on a sample of peak flows. And this sample was selected according to two different options, annual maxima, peak over threshold. But still, we need to estimate a probability distribution. To close this topic, let me say that we need to make one final remark. The final remark is related to the fact that I made a premise at the beginning of our lectures. I said any method, any hydrological model should be physically based. So your question could be, what is the physical basis here? Because if I fit a probability distribution, this is a probabilistic method. And probabilistic means that it uses the theory of probability. Remember that probability is different by statistics. With statistics, you analyze data. With the probability theory, you estimate the frequency of occurrence of events. So when I say probabilistic, I mean that we estimate the frequency of occurrence. And you may say, what is the physical basis? I just get numbers. The numbers may represent floods or may represent potatoes. There is no connection, you may say, with the physical phenomenon leading to the flood formation. I think this is not correct. This is a matter of interpretation. But if one said that fitting a probability distribution is ignoring the physical basis, this wouldn't be, in my opinion, correct. Because there is indeed a physical basis, a physical information, which is brought into play by the data. You get data that indeed refer to floods, not to potatoes. And these data bring the physical information about the phenomenon. You are not explicitly using the physical information. The physical information doesn't appear in your equations, because the equations that you use